All right, so let's turn back to page 312 for just a moment, and this take a look at that first couple paragraphs on page 312. Okay, it says in the laboratory reaction is carried out with exactly the required amount of each reactant, and I'm thinking that when we go through and calculate how much you theoretically should have come up with, it's probably going to be anywhere from 6 to maybe 10 grams. And when you measured that, I'm guessing the amounts probably varied from probably 1.5 to 2.7 grams of actual product. Did anyone have under 1.5? Okay. Did anyone have over 2.5? Okay. And that's what we would expect. So we'll get to that here in just a moment. Okay. In many cases, one or more reactants is present in excess. That is, more than the exact amount required to react. Once one of the reactants is used up, no more product can be formed. The substance that's completely used up in the first in a reaction is called the limiting reactant. The limiting reactant is the reactant that limits the amount in order of the amount of the other reactant that can combine the amount of product can form in a chemical reaction. Then the excess reactant is what you would have left over. So the example that we had given is if you're playing basketball against a taller team, you're limited on what you can do on offense. I think you would agree with that. Or if in football you have a select amount of injuries to where, I don't know, the right side of your offensive line is just decimated with injuries. So you have backup upon backup. You don't want to run right because personnel in there is not used to it. So you're limited to what you can do. So in this case, this is what we're referring to. The reactant that runs out first, okay, is therefore called your limiting reactant. It limits what you can do. It doesn't mean that the reaction is not going to take place. It's just limiting on what you can actually produce. And in this case, it's that precipitate that you measured. Okay? So let's say, for instance, you needed to have 7 grams of product. Notice a lot of you came up short with that. I mean, chances are you probably could have received more of a product, but what was possibly the problem, in your opinion, with trying to get more and more of that precipitate out? I mean, a lot of you did your best. You're taking those, wood splints, is that what you would call them? So that's going to be difficult, and how long it takes for that water and the precipitate to go through that filter paper, that takes a long time. So in ideal conditions, you could maybe stand there all day and scrape it, and rinse it, and scrape it to bring that percentage up a little higher. But we don't always have that capability or that option. Okay, so when we're talking about a limiting reactant, you're just referring to which one runs out first. So on page 313, in the practice problem section, it talks about all of those, the limiting reactant, the excess reactant, and then how much of a product then is formed. So in the practice problem on 313, some rocket engines use a mixture of hydrazine, N2H4, and hydrogen peroxide, H2O2, as a propellant. The reaction is given by the following equation. Okay? And notice that it is balanced for you. So we have N2H4 and then you're adding this hydrogen peroxide, and then that will give you or yield nitrogen and water. And then what they do for you is they balance it. So I think there's a 4 there, and then what, a 2 here, so 4 and 4. Yep, that would give you 8. All right. So in letter A, just goes through and says, which is the limiting reactant in this reaction when 3/4 of a mole of hydrazine is mixed with half a mole of hydrogen peroxide. So what you go through and do is if we have 0.750 moles of this substance and 0.50 moles of that substance. Okay. There's one of two ways you can approach this. One, we said that battleship analogy, where you're just working with the left side of the equation. You can do that for finding your limiting reactant. Or you can pick one of these products and find out if you have this much substance, how many grams of nitrogen or even moles of nitrogen would you make? And then you'd have to use this reactant, see how many moles or grams of that product you would form. When we did this earlier, and I would expect some people to say, yeah, I just flat out did not get that. Is there any area that looked more appealing or more easier to do than the others? If you can remember, this is probably the last, Wednesday? It was over a week ago we did that. Does that sound accurate? Maybe yes, maybe no. But what do you think would work best for you? Or maybe you don't know. Or should we just pick a way to go through and then you can decide for yourself? That one? Okay. So what we need to have you do then is pick out, which product would you like to deal with, the nitrogen or the water? You are going to have to pick one of them. Nitrogen? Okay. So what we're doing is we're going to take 3/4 of a mole of hydrazine. And we're going to convert that to moles of nitrogen. Okay. So when we do this next step, notice we're going to have a mole over a mole, which means you have specifically called a what? You have a mole ratio. And when that happens, you have to go back to your balanced chemical reaction. So for every mole of N2H4, we receive a mole of nitrogen. And notice we've got 1 in front of each one, so that's where we would stop with that. So in this reaction, we're going to get 0.750 moles of nitrogen. Okay? So do we know which ones are limiting reactant yet? Well, no. Because we have to take both of these, and you had picked nitrogen to work with on the right-hand side. So we take 0.50 moles of H2O2 and convert that to moles of nitrogen. So for every mole of nitrogen, we get 2 moles of hydrogen peroxide. So in this step, okay, is anyone confused with how we're getting from step 1 to step 2? Because notice you're canceling out your factors in both steps. And once you get in that upper right-hand corner where there's 2 steps, 3 steps, or 4 steps, when you get that in this process, then you know that you're done. Okay? So, why is that there? Yeah, because it's a mole ratio, that coefficient 2 is up there. So when we multiply that out and divide, you would only get 0.250 moles of nitrogen. Okay? So when we look at that, what does that tell you your limiting reactant? Which one would produce less? Yeah. So when you do that, and this is another aspect I would suggest that you do, is once you have determined that, you say, I wouldn't care where you did that, but somewhere around that compound put LR. So you always know you're referring back to that limiting reactant, because if we're concerned with how much water we're producing or how much nitrogen we're producing, okay, this would certainly produce that in excess. Your hydrazine would, because you have plenty of that. And you might run short on this without even knowing it, okay? So that's why it's important to go through, and you're limited on how much nitrogen and water you produce because that's your limiting reactant. Kind of like if you're the right side of the line we just talked about, or if your average height for you ladies is, I'm going to say, 5'7", 5'8". Okay, so if you are, we're gonna say dream big or imagine big. That I'm just gonna throw this out here. Seems like is it Bridge? No, Ethan. Was it Ethan over there by Bridgewater? Had a really good girls basketball team last year. And they made it state. So we're just going to use them as an example. Maybe they're good this year again. Maybe, but their average height is, we're going to say 5'10", maybe 5'11". So you might be limited on what you can do inside because of just the height difference. Okay, so it doesn't say that you're not going to be able to be successful, which we know you're capable of. So just keep the ball rolling. You survived practice yesterday. Was there any worries that it might be, ooh, this might not be fun? But you made it. Very good, very good. So that's one that you could do. Okay? Well, not everyone's going to pick the same product. You could also go through and do that of water. The only thing that you would have to change then would be this. Instead of doing nitrogen, we're doing water instead. And in that case, for every mole of N2H4, we would get 4 moles of water. And in this case, for every half a mole of hydrogen peroxide, we would also get 4 moles of water. It doesn't matter which one. It's just one of those aspects to where if you're working on a paper and you're checking with a classmate saying, well, I came up with this answer, okay? When you're comparing these numbers, you may have chosen nitrogen. Someone else may have chosen water. So that's the only thing you'd have to be careful of, because not everyone's going to pick nitrogen. Not everyone's going to pick water. So in this case, let's see here. So does this come out to be like 4? No, doesn't sound right. 3? 3 maybe? 0.750 times 4. Yeah, give you 3. So this gives you 3 moles of H2O. And in this case, 2, that would just give you 1, right? Same result. This is going to limit on what you can do. So that's another aspect that you can do. Or the final one, like we did last week, was do this battleship analysis, where you see how much you actually have and to determine how much you actually need. Do you feel you want to see that third option? Yes? No? Because we're not going to go into that if you feel comfortable with this. So middle, are we good? Okay, right outside. Okay, left middle. Right middle. And left outside. Okay. So then what happens is as we read on, okay, H2O2, we already determined that. That's our limiting reactant. And again, please label that when you get some of these assessments and problem solving. Letter B says, how much of excess reactant in moles remains unchanged? Okay, well, in this case, we would have to go back to so this is how much you had, and to do our excess reactant then, then what we would do, back to this, when we do that reaction, okay, so if we have 3/4 of a mole, okay, and we're staying on this side of the equation, so for every 0.50 moles of H2O2, we need to see how much of this was required. So when we do that, okay, for every 2 moles of H2O2, we get a mole of N2H4. Okay, so now when we take 0.50 and divide that by 2, we get what? You have 50 cents. Take those 2/4, they get split in half. So if we've used 1/4 of a mole and we had 3/4 to start with, you subtract the 2, so how many moles would you have left over? You had this, you burned through that much, so you have how much left over? 0.5. So notice, what does it say right here? 0.50. Okay? We can trust this gentleman, can't we? Are you trustworthy? Okay. Was that a yawn or is that a no? Oh. Sure, right? So yes, half a mole would be what's left over. Then, how much of each product in moles is formed? Now, so are you going to start with N2H4 or H2O2 to see how much of each mole is formed, of each product is? Say that again. You are right. Why are you right? I bet there's a better reason. We said, I can't stress this enough on why you want to do this. You know, be a little more confident. Say that again. The limiting reactant. That's why we put this up here. So if we've determined that this is our limiting reactant, that will determine how much of this can be formed in moles. Okay? And we've done that already, even though I erased it. We get a 1/4 mole of nitrogen and 1 mole of water. And you have that written down already, correct? Those of you who chose to, and that's fine. Do you feel you need to see another example? Yes? No? Or do you feel comfortable with this? Asking for input. The input I got is we're good. We're pretty comfortable. Let's see a thumbs up. We're good? All right, so the remainder of the time then, what we can do, we could say, who's going to win the lottery here and who we pick to utilize as a group as an example. Okay? Well, see, you're just that quick. You're the one that raised your hand. Okay? So, with that being the case, okay, then we'll wrap this up. Then the rest of you can go ahead and we'll calculate your percent yield. So, we know in this process we had some silver nitrate. Okay? We reacted that with some sodium chromate. Okay? And in this double replacement reaction, I think we have to have a 2 there, plus NaNO3. Okay? So, everyone should have this written down. Not everyone, but if you're sitting there, your lab partner should have this, or lab partners should have this wrote down. So, back corner, can you confirm this? We at least have this. Okay, so what coefficients do we need to balance this? Well, we've got 2 silvers here and only 1 over here, so what do we need? Okay. Now we've got 2 nitrates on the left and only 1 nitrate over here. So what would we do? Put a 2 here. So now we've got 2 sodiums. Oops. We got 2 sodiums there. 1 chromate, 1 chromate. Now we've got it balanced. Okay. So, how many grams of silver nitrate did you start with that you measured on the scale? 2.0? Exactly. Okay? So 2.0 grams. What about your sodium chromate? Okay? Here, I was waiting here, 7.0. But no, that's fine. We said if it's over 7, fine. Write it down. If it's over 2, fine. Just make sure you're writing that down. Okay. So, we can do a little bit of foreshadowing here. Nitrates are really soluble in water, so you're not going to see that as your precipitate. Here is your precipitate. Okay? So we're going to knock 2 birds out with 1 stone. So we're going to want to find the X amount of grams of this eventually. And to help us in the process, rather than just picking one of the reactants, taking these and converting only to moles of that, we'll just go ahead and change to grams of that. Because that's something you're going to have to do anyway, because we want to find out what your percent yield is. Okay. So, if we need to refer to this example, that's fine, but what would we do with this? We're going to take 2 grams of silver nitrate, okay? We're going to do a 4-step problem, okay? So we need to get from this side of the reaction to this side, okay? So how do we get that grams of silver nitrate to cancel? Okay, so for every gram of silver nitrate, we get 1 what? A mole of silver nitrate. Now, remember, it's fine to abbreviate that, just as long as you know that it's standing for that formula. Because we need to put the atomic mass here. I think it's about 160, 168. Okay, 169.88. Okay, so these grams have canceled. We're in moles of silver nitrate, so remember, now we're going to hop to this side of the equation, and that mole ratio allows us to do that. So, how do we cancel this mole of silver nitrate out in the next step? On top of the bottom. Okay? So for every mole of silver nitrate, we could get a mole of what over here? Yeah, chromate. Okay. And remember, that's Ag2CrO4. That's silver chromate. But we've got a mole to mole ratio. So that means we've got to go back to our equation. Are there any coefficients? Okay. So the silver nitrate has a 2 there. So we put that here. These have now canceled. We're in moles of silver chromate. We're on the final step. Okay. So for every mole of silver chromate, we get a certain amount of grams of silver chromate. And how many? 223.87. These have canceled. We're in grams of silver, silver chromate, and we're looking for that. So when we multiply all them out, okay, so if we take 223.87 times 2 gives us 447.74. Still have to divide that by these two times each other. 69.88. Okay, so once we divide them out, 447.74 divided by 339.76. So that gives us 1.32 grams. Okay. So 1.32 grams of silver chromate. Now, that's if we're starting with silver nitrate. So we've got to do the same thing. Now, a lot of these numbers, we can just kind of take a shortcut by saying 7.08 grams of sodium chromate. Well, maybe better write that out because we got SC over here for silver chromate. Okay. So for every gram of silver chromate, we get a mole. So for every mole of sodium chromate, we get a mole of silver chromate. And I guess I'll leave that there. And then finally, for every mole of that, we get 223.87. So, notice in front of here and in front of here, do we need any coefficients down here? And I'm going pretty fast. Are we going too fast? Okay, so do we need any coefficients down here? No. So the last thing we need to do is add together these atomic masses. So, let's see here. And chromium is at 52. Okay. About 162 grams per mole. So, 162. All right. So now when we multiply these out and divide by that, okay, 7.08 times 223.87, divide that by 162, 9.78. Okay, well, which one is your limiting reactant, do you think? Is it this or is it this? Silver nitrate. Then, what we suggest that you do is up in the reaction, do what? What do we do in the top one? Label it as, put LR by here. So anytime you have to refer back to this, we know that silver nitrate is our limiting reactant. Okay. So, on pencil and paper, according to this reaction, theoretically, how many grams of that silver chromate should we make? Theoretically. So, do we really need to keep this bottom one? You're shaking your head. No, you are correct. Why are you right? Because this is your excess reactant. Remember, we need to go by your limiting reactant. So this one, we can now erase. Said we're going to do two things at once. One, we're going to determine our limiting reactant. We did that. Two, okay, is that Morse code or is that someone's phone? Okay, or both, I don't know. Okay, so theoretically, okay, we should produce 1.32 grams. How many grams did you actually produce? Really? Is this right? Because if you do that, remember, percent yield is what you actually produce divided by what you theoretically should come up with. Theoretically, we should get 1.32. So if you're saying you got 2.0, that's over 100%. That's what I thought, but I hadn't worked that far ahead. Okay. All right. So again, you had produced 2 point what grams? 2.00 grams. Okay. This isn't working out how I would have thought that this number would be bigger than that one. Okay. So, so you had calculated this out to be around this number too? 2 grams as well? Oh yeah, you did say 1.59. You got... Okay. Yeah, that should be right. That's 107. That's 14, and that's 48. Okay, so that's right. And with this, oh, did I tell you this was the right number? It's 330. I got 330. This isn't one of them saying, gotcha. No, 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 that's not what we're trying to say. Let's just make sure we're on the same page, okay? That's 107, right? Okay. All right. So put 330 in there then. 330. Not just the time that we're hoping it is. So 330. Okay? That should drive that number down a little more. Makes it feel a little better. So go ahead and look through there, and we'll make some adjustments for tomorrow. Because tomorrow we'll talk about percent yields, like what we're doing here, and then we'll get you on your merry way with worksheet 4. Okay, so we'll catch up to you next time.